component that involved in the frequency change. I mean, usually if we have signals with different frequencies, and we have some unwanted signals or some noise we want to remove from the signal or from the data signal or from information signal. So we have to use such device or such filters. Okay, so filter is a circuit which used to attenuate certain frequencies. So I know, for example, when I send the signal from the transmitter to the receiver, the transmitter already know what is the frequency of the sent signal or the data, but the receiver when receive the data will receive the signal with different frequencies. So there is the signal which carry on the data, and there is another signals which come from the surrounding environment or interference from other devices and so on. So this signal represent noise. So the filter circuit will be used to remove such unwanted or undesirable signals. So it consists at least from one pass band. When we say pass band here, that means one frequency which allow to pass the signal from certain point to another point. So we need to define, when we say band, that means we need to define 2 points. I mean the minimum point and the maximum point. So each filter should have these 2 points. I mean the minimum point to allow the signal to go, the maximum point to allow the signal to go, okay, or to pass through. There is we have one parameter, we call it cutoff frequency. So the cutoff frequency here is the most important frequency for the filter, whatever is the filter type, is it low pass, high pass, band pass, whatever, but each one it has some frequency or a value of frequency. We call it the cutoff frequency. So cutoff frequency means the frequency at which the signal will not be allowed to go through. Okay, so for example, cutoff frequency for low pass starts from usually the low pass is 0, then is go to the cutoff frequency. So before this one is allowed, after this one is not allowed. So the FC here or cutoff frequency is the value of frequency. After it, there is no more signals, or the value of frequency before it, there is no more signals. So it is a cutoff value. And this cutoff frequency usually depends on the component of the filter. Since our filter is a circuit, when we say circuit, that means circuit, it has element or component, resistor, capacitor, inductor, power amplifier, whatever is the components. So represent the circuit or connect in the form of the circuit to form our filter. Okay. So usually we have 2 main category of the filters, 2 main categories, no 2 main types, 2 main category. The first category we call it the passive filters, and the passive filters here is consist from a passive component. So passive components like resistor, capacitor, inductor. Passive component, that means component which which store or dissipate the value of the power. So it's not produce a power, it's just take a power from the power source. So for example, the resistor, the capacitor, the inductor, they have to be connected with the source in order to store some type of energy or dissipate some type of power inside this component. The second type, we call it the active filters. So the active filters here, it has some active elements. Active element, that means element which can produce or can impact, have an impact on the value of the voltage, the value of the current, and so on, like the operational amplifier. As you study in the electronic part and the electronic course, operational amplifier, for example, is an active element. So when you connect the operational amplifier with the voltage source, this operational amplifier has a gain value. So this gain value can amplify the input signal, or by certain values or certain gains. So active filters usually have such operational amplifier, like operational amplifier for addition and operational amplifier for subtraction, for division, for integral, for derivative, whatever is the operation required from this amplifier. But the active filter should have such element inside the circuit of the filter. In terms of the type, both active and passive filter, they have different types. The most important part, so there is more extra types here, but the most important part or the most common type is this four types: low pass filter, high pass filter, band pass filter, and band stop filter. You can see here pass, 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 and here stop. So in the first part, which is the low pass filter, the signal or the filter will allow for signals or for frequency from 0 to cutoff frequency to pass through the filter, while the other signal will be removed. As you can see here from this graph, so this is the low pass filter here. In the low pass filter, it allows for signal from 0 until FC or cutoff frequency here to go through the filters, while all the other signals will be 0. I mean, if the signal has a frequency greater than cutoff frequency, so it will be cut off or will be removed. This we call it the low pass filter. So the output signal will only the signals with the frequency in the range from 0 to FC. So FC here can be if we talk about FC in hertz or in radian per second, whatever, I mean in radian per second. So in both cases we have minimum is 0, maximum is FC or cutoff frequency. In the case of the high pass filter here, we have also cutoff frequency. We said each filter should have this value. So the cutoff frequency here, I mean all the signal before the cutoff frequency, I mean if the signal has a frequency less than FC, so it will be removed. While all signal with frequency greater than FC, it will be passed through the filter. Okay, so if I apply a signal with a frequency, if we say this one is 100 kilohertz, for example, and we apply the signal, we use the signal generator generation to produce a signal with a frequency of 90 kilohertz. Then we connect to this filter, to such high pass filter. So, and we define the carrier the cutoff frequency of 100. That means this signal with 90 kilohertz will not pass to the output of the circuit. So this is the filter, for example, consists from different element R, C, L, or operation amplifier. Then I have here the signal generator, will generate the signal with the certain frequencies, and here I have the output that I want to connect to our load, for example. So if the frequency is less of this signal generator is less than the cutoff frequency, so it will not pass here. So the no signal will be, no output will be given on this load. If the frequency of the signal generator is greater than FC, it can be up to infinity. Whatever is the value, 100,000, 2,000, 10,000, 1 gigahertz, 1 terahertz, whatever is the frequency, so it can pass to the output because it is high pass filter. It allows to the high frequency to pass through the filter. The third type, which is band pass filter. So the band pass filter, we have a band, and usually the band is defined by two values, minimum and maximum. The same here for the low pass and high pass. The low pass, it has minimum is 0, maximum is FC. The high pass minimum is FC, the maximum is infinity. Here in the band pass, you have two definite values. We call it the cutoff frequency, the lower cutoff frequency and the higher cutoff frequency, or cutoff frequency 1, cutoff frequency 2, FC1 and FC2. So we are going to say, for example, this filter will only allow for certain bands of frequencies to pass through the circuit. So for example, if I have signals from 0 to 1 megahertz, this is all the range of frequency that I have. And I want only the frequency between 400 to 600 kilohertz to pass through. 400 kilohertz to 600 kilohertz. So in this case, I have to use such band frequency because I know the minimum frequency, I know the maximum frequency, and this is minimum is 400 kilo, this maximum is 600 kilohertz. So in between this value, all the signal will go through our system. While the frequency which is less than 400, which is from 0 to 400, will be removed. The frequencies from 600 until 1 megahertz will be removed. Only the frequencies on these two bands will be passed or go through the filter. The last type, which is band stop filter. So the band stop filter here, it has a band, also definition for band, minimum value, maximum value, but in between these two values, we do not have any allowed frequency here. So the attenuation, we call it the attenuation band. So band stop, that means band attenuate also. So attenuation band here, it has two frequencies. All the frequencies less than FC1 will be go through the filter. All the frequencies which is higher than FC2 will go through the filter. But all the frequency in between FC1 and FC2 will be removed or will be excluded from passing through to the output of our circuit in this. Okay, so this we call it the band stop filter. There is also all stop filter. I mean, which attenuate all the type of frequency. Just we wanted to. There is also all pass filter, which allow to all filter to pass through. But sometimes we need such type of filters just to make like buffering stage, and I mean to allow to the frequency to go from one part of the circuit to the another part of the circuit. So these are the main types of our of the filters that we are going to cover in this chapter. What our task will be later on, we are going to see how we can find or how we can define the cutoff frequency. So if we know the cutoff frequency for the low pass, so our allowed frequency or the allowed the desired or the frequency that will be allowed to be passed through the circuit will be from 0 to FC. If I know FC for the high pass, that means all the frequency from FC to infinity will be allowed, but all frequency less than FC will be attenuated or will be excluded. Band pass filter, I need to know FC1 and FC2. So others than that, it will be removed. Also the same for attenuation here. I need to know FC1 and FC2. And in between these two values, it will be attenuated and others will be passed through the system. So this is more, I mean, the definition for each explanation about each type for low pass filter, high pass filter, and band pass filter, and also band stop filter. You can just go through the same thing that we already explained. What is the difference between active and passive filter? So for active and passive filter here, we said it depends on the component for each type of the filter. And we said that passive filter is use some of the passive components like resistor, capacitor, inductor, while active filter it uses some of the active component like operation amplifier. So the main here there are some advantage or disadvantage for both type here. So the passive filter here have some of this disadvantage of drawbacks. So the passive filter, they cannot create a gain because greater than one. Because if you have a resistor and capacitor, we cannot generate a gain like in the case of operation amplifier. So the active filter is more flexible in the gain values. So we can adjust the gain of the input signals. So it can be increased or decreased, depends on the requirement of the signal that will be sent through the filter. Then also doesn't work well for frequencies below the audio range. That means for the audio range here, there is some certain frequency for the audio range. So the passive filter is not desirable to be used in such range of frequency because it's not more accurate. It requires inductors because we said the passive frequency, the passive filter, it consists from R, L, C. So it requires the inductors, and inductors actually it comes with a very big size or bulky size, and also it's too expensive comparing with other components. If the L is expensive, that means the cost of this passive filter will be more expensive comparing with the active filter. So how to solve this issue? We go for the active filter. So active filter can use operation amplifier to create some of the type of the filter, and it can this operation amplifier can provide with some of the gain and frequency adjustment more flexible because we have the gain of operation amplifier, so we can adjust the gain. With adjusting the gain, we can adjust the amplitude of the signal, and we can have more flexibility in changing the gain and also the frequency of the signal that we want to send. No loading problem, because the operation amplifier, it has a very high input resistance and very low output impedance. So this will make it has low output impedance or resistance, and it has high input resistance impedance. So it will not generate more current to go through the load. It will not cause more losses in our circuit. So these two are among the advantage of the passive, of the active filter that use the operational amplifier. The third is on the cost. As we already mentioned before, we said in the passive filter we have to use the inductor, and the inductor is a bulky size and also it's expensive, while the operation amplifier, it has very cheap cost. So we can build our filters or design our filters with small or with low cost for the filter circuit, since there is no inductor anymore. So now we are going to have one by one of this filter to know how we drive, or how we can calculate or find the frequency or the FC value here. So usually the typical low pass filter here, if we start with low pass filter with the first type. So in the low pass filter here, it can be formed from RC circuit. RC circuit means if you have resistor, capacitor, and connect to the voltage source here, so you can form this represent the filter circuit. How? By taking the output across this resistor capacitor. So it's not taken from here. You take the output from the capacitor. So in this case, this circuit represents the low pass filter. So it will allow for frequencies from 0 to FC or to omega C to pass through the circuit, while frequency greater than omega C or FC will not go through the circuit. What is the value of this frequency? As you studied before, when you study the capacitor, how to charging and discharging the capacitor, if you remember. So we have some parameter, we call it tau, or time constant. It's almost the same like this value here. So it's omega C is equal to 1 over RC. So the value of the frequency here that we are going to, or the cutoff frequency for the low pass filter, is equal to 1 over RC. R represents the value of the resistor, C represents the value of the capacitor. So you have R, you have C. If you know the value of R and you know the value of C, you can easily find the value of the cutoff frequency here, omega C or FC. Okay, so we talk here about omega C equal to 2 pi FC. So as you can see from this figure here, usually they call this frequency, the cutoff frequency, they call it the, the frequency which required to produce the half power frequency. Half power frequency, this one, the value that half power frequency usually is like -3 dB. They use it as a standard value to decrease the power from the maximum value or from the highest value to the half of its value. So the power of this point here, which is for the maximum value, in order to reach to the half of this power, we need to use the cutoff frequency equal to 1 over set 2 or 0.0707. Okay, so this graph represents our magnitude for the transfer function. So the transfer function here gives you two values. One at 0 is equal to 1, and at omega C here is equal to 1. Then at infinity will equal to 0. After omega C, whatever is the value of omega here, H omega will give you 0. Only H omega has the values between 0 and omega C in this range. Here we have a magnitude for our transfer function. Whatever is the output here, whatever is the other frequencies, H omega equal to 0. That means our magnitude for the transfer function will equal to 0 when omega greater than omega C. For that, we call it low pass filter. Only this value or this area with omega less than omega C, we have some of the output or magnitude for our transfer function. And we said when we have transfer function, it's a relate between the output and input. Here is the input is V in and the output is V out. If we want to drive the transfer function for this circuit, we need to write the relation that that connect between the V out, and which is the voltage across the capacitor, and the V in, which is the voltage of the voltage source. As you can see here, this is how we can derive the value. So as you can see here, the magnitude of H omega C for the half of power is equal to 0.707. This, as we mentioned before, we say this like standard value to decrease the power from to its half or to half of its value. So the power or the magnitude of transfer function at omega C is equal to 1 over Z2 or 0.07. H of 0 from this graph, as you can see, H of 0 is equal to 1 and H of infinity is equal to 0 because all value here are equal to 0. So we have these three values. We have 1 over Z2, the one that which is here at the half of the power here, the power signal. Then the H0 which equal to 1, H infinity which equal to 0. Now, how we can find the transfer function for our circuit, which consists from voltage source. This is voltage source V in. This is a resistor, and this is a capacitor. This is the voltage source V in. That means it's become like V in of S. This one is V out of S, which is at the capacitor here, and the capacitor value will become 1 over J omega C. We said R in the time domain gave you R in the frequency domain. L in the time domain give you L S in the frequency domain, and C in the time domain gave you 1 over C S in the frequency domain. When we have C is equal to J omega, because we in this chapter we said our focus more on the omega and J omega here. So we are not talking about the S domain. We talk about the frequency domain, the exact value of omega. So this value will be represent C. I mean S will become like C will give you 1 over C times J omega C. So it will be like J omega C. Okay. So 1 over J omega C. Replace S by J omega. So it's become like C J omega. Okay, this is the one that we have here, J omega C, either C, J omega, but we talk about this one is the imaginary operator. Usually it's go out, so it's become like J omega C. This is for the capacitor. Now we have R here, R becomes still R. Now how we can find the relation between the V out and V in of this circuit? By using the either Ohm's law or by using the KVL, KCL, whatever you can use, so you will get the same result. The relation here, if you want to write this equation here, so you need to perform two tasks. First, you need to find the transfer function. Then, the second, you need to find the, you need to find the transfer function. Then the second, you need to find the value of omega C. So the transfer function, we said you have this one element circuit consists from one source input and two elements here. So if you want to find the transfer function, first you need to convert each element from time domain to frequency domain. So this one V in of S, this one V out of S, this one still R, nothing changed. This one become 1 over J omega C. Then you write the equation by using KVL, which is V in is equal to IR plus the V out. Because actually this is V in is the input source. So the output will be, or the voltage drop will be VR. If we said like this one, plus, minus, VR. This one is plus, minus, V out. So this become plus, minus. So you go this side, it will be like V in minus IR, VR. Minus VR minus V out. The equation here will be like this one. V in, if you want to write it in one side, V in plus minus VR minus V out is equal to 0. Then this can be changed to other side. So it's like V in is equal to VR plus V out. Now you need to substitute for VR by its value, V out for its value. So V out here, give it here because we need it in our transfer function. VR will equal to IS R, but IS here is equal to V out over J omega C. So it will be like J omega C V out. So you substitute for VR by R times G omega C V out. Okay. We said like we have V in of S equal to V out, equal to VR, which is the voltage across R, plus V out, which is the voltage across the resistor. This is how we write it. Or it can be like this one, the original one, V in minus VR minus V out equal to 0. So this using that KVR. Then we substitute for the value here. So V in stay V in equal to VR, which equal to R times IS plus V out. Then we said we already find IS equal to the value of the V out times J omega C times V out here. Why? Because it equal to V out over the capacitor impedance. Okay, we substitute for IS here, so become V in of S equal to R times J omega C V out S plus V out. Now we take the V out outside, V out of S outside. We have here R or J omega C R. This is V out plus V out here, take it outside already 1. So this is the V in of S. Then we have V out of S over V in of S is equal to 1 over J omega C R. This is C, not omega C, this one. It's not the J omega C. Omega, that means omega times C, okay? Omega R plus 1. So this is the transfer function that we have. So V out here over V in, this represents the value of H of omega. This is the transfer function. So H of omega is equal to 1 over 1 plus J omega RC. So this is how we can find this value. Okay, then you substitute for omega equal to omega C. The magnitude at omega C is equal to 1 volts over 2 from here, and we solve like we did before. This is the proof for the omega or the low pass filter transfer function and the frequencies. So what you need, you have this 1 over set 2 is equal to 1 over set 1 plus omega C square R square C square. Okay, if you make square for both sides, this you have 1 over 2, then you have 1 over 1 plus omega C square R square C square. Then you cross multiplication here, so you have 1 plus omega C square R square C square is equal to 2. Then omega C square R square C square equal to 1, because this will go the other side, 2 minus 1. Then omega C square will equal to 1 over R square C square, or omega C will equal to 1 over RC. So this is how we can calculate the value, or how we can prove that the omega C here is equal to 1 over RC from this set. You need to know here, from low pass filter, you need to know that the cutoff frequency is equal to 1 over RC. This is the formula, and H at omega C is equal to 0.707. H of 0 is equal to 1. H of infinity is equal to 0. So these are the main characteristic or main features of the low pass filter. If you have H of 0 equal to 1, H of infinity equal to 0, that means this is a low pass filter. If you have h of infinity equal to 1, h of 0 equal to 0, so this is will be the high pass filter, as you will see later on. Okay, so this is for the high pass filter. The same component for the low pass and high pass. Here in this case it is the same, it uses RC also, two passive component, but the output here taken across the resistor R instead of the resistor, I mean the capacitor C in this case. Here the output is taken across C, but here is the output is taken across R. So in this case it is a high pass filter. This is how the high pass filter looks like. So the high pass filter here, all the frequencies less than omega C, no value, 0. In the ideal, we are talking about the ideal case. This is the practical one. There is some value which is small, but in the ideal case, this is equal to 0. I mean, for the ideal filter. Then, more than omega C, there will be a value here. What is the value of I mean, for the H, omega C is the same here. The cutoff frequency value will give you half of the power, which is 3 dB. I mean, negative 3 dB. So this is equivalent to 0.707 here. H of 0 is equal to 0. H of infinity is equal to 1. So this is for the high pass filter. This is the main characteristic for high pass filter. So how we can find the omega C value here? Omega C is equal to 1 over RC. It is the same as the previous one, 1 over RC. The cutoff frequency for low pass filter is the same as the cutoff frequency for high pass filter. It depends on, only the difference is from where we take our output. Is it from the capacitor? So it is low pass. Is it from the resistor? So it is high pass in this case. So this is the derivative, same like we did before. You need to redraw the circuit in the frequency domain. You need to assume V in. So you can say like this one is V in of S minus VC, which is the voltage across here. This plus minus, for example, this is VC plus, I mean minus V out equal to 0. Then this will be go to the other side, and you need to substitute for the value of VC here by the value of the current, which equal to the current over the capacitor. So then you leave the V out as existing there in order to find the relation between the V out and V in. Don't omit, when you calculate the transfer function, you have to keep V in and V out there. You need to remove the other part which is not related to V in and V out. You make it related. So for example here, VC is not related to V out, is not related to V in. How we can substitute for VC by some value which depends on V out? We need to have the value of the current, then the current will be the same on the capacitor and also on the resistor. So this will be the cutoff frequency for the high pass filter. For the band pass filter here, we have a band pass filter, which we said in the band pass filter, we have two frequencies, which is like FC1, FC2, or omega 1 and omega 2, which define the band of these frequencies. So that means the signal between omega 1 and omega 2 will be allowed to pass through the filter, while signal less than omega 1 or greater than omega 2 will be removed or excluded or attenuated to be not taken from the output of the filter. So as you can see, this is the design of the, or this is the structure or design of the band pass filter, which L, C, R, and the output will take from the resistor, which have inductor, capacitor, resistor, and the output will be taken from the resistor. As I told you, the filter is not just, I mean, this is the most common form, which RC or CR and so on. This is the most common form, but you may have some low pass filter with RCL. You may have some high pass filter with RLC. Okay, it can be, and who will decide is it high pass or low pass? It is the features here, these values. The value of the magnitude for the transfer function. If it is 0, 1, in this case, it will be high pass. It is 1, 0, so it will be low pass filter. So this is how the, I mean, the operation of the low pass will be go through. So in order to find the transfer function, you need also to write the equation. So for example, here you have V in. Your equation will be like in this form, like this one: V in of S minus VL. Why V minus? Because this is the only source in our circuit. Minus VL of S minus VC of S. This is the voltage across the inductor. This is the voltage across the capacitor. Minus VR or V out is equal to 0. Then you need to find VL and VC. You need to substitute by some value, depends on the current, because you have, if you have IS here go through this circuit, this IS will go through all elements. So IS for the inductor is the same as the IS for the capacitor, is the same as for the IS for the resistor. So IS here is equal to V out over R. So you just substitute for IS here, V out over R, IS here, V out over R, and you can find what is the transfer function for this circuit. Here is the derivative here, V out over V in, which R over J omega L plus 1 over J omega C. This is for the inductor. This one is for capacitor, and here you have for the resistor. From this derivative here, you can find that omega out is equal to 1 over set LC. In the first case, it was 1 over RC. The second 1 over RC, here we have omega naught is 1 over LC. This is not the cutoff frequency. This is the center frequency of the bandpass filter. Center frequency means it is the value between omega 1 and omega 2, this value. So if I want to find omega 1, it will be omega naught minus the band between them over 2. Omega 2 will be omega naught plus the band pass here over 2. That means this omega naught plus this part, this omega naught minus this part. For the band stop filter, also it's the same RCL, but the output here will be taken across the two element, which is the capacitor and inductor together. And also it has, when we want to calculate the transfer function here, we need to find the value of omega naught. And omega naught here in this case will be the same as the band stop filter, which is 1. And this one we call it the resonant frequency. If you remember for resonant circuit. So resonant frequency here, 1 over LC. Same here, 1 over LC. So the band pass filter and band stop filter, they have the same resonant frequency or center frequency here, which is omega naught equal to 1 over LC. And the band pass filter here, it has H0 is 0, H infinity is 0. Why? Because only it has in this range here. But at the 0 point, there is no magnitude. At the infinity point, there is no magnitude. Okay? So this is, if you have H0 equal to 0, H infinity equal to 0 for your magnitude of transfer function, so that means you have a band pass filter. For the band stop filter here, the omega naught value is the same. The omega 1 is the same, omega 2 is the same. Only the difference here will be in the H0, there is 1, H infinity, there is 1, and H in between this one will be 0. So you can see here the magnitude. The magnitude at 0 is equal to 1. The magnitude at infinity also is equal to 1. As you can see here, these are, if you have such values, that means this is band stop filter. H0 equal to 1, H infinity equal to 1. Previous one, H0 equal to 0, H infinity equal to 0. This is the band pass filter. So these are the main characteristics that from it you can identify. If the question is what is the type of this filter, you need to identify based on these values. How to find these values? You need to find the magnitude for the transfer function. You will be given you can calculate the transfer function. From transfer function, you substitute for omega by 0, substitute for omega equal to infinity, then you find it as we did before when we find the initial and finite values in the Laplace transform chapter. So this table summarizes all the characteristics of the filter or the ideal filters here. For the low pass, it has H0 equal to 1, H infinity equal to 0, high pass 0, 1, band pass 0, 0, band stop 1, 1. And these are the value for omega C or omega naught. Omega C is the cutoff frequency for low pass and high pass, Omega naught is the center frequency for the band pass and band stop filter. Okay, we're going to